And our next speaker is Jérôme Gros from Institut Pasteur. And we're going to move now from flies to chick or quail embryos. And he will tell us about the mechanical control of avian gastrulation.
Okay, thank you very much, Thomas, for a very kind invitation to a great meeting. So we are, as many of you here, interested in morphogenesis, and we are use avians here. And what you're looking at is the first day of a quail embryo. It stops, but I'll go back to that. So, and what we're trying to understand is how gastrulating embryos are shaped during development. So, yeah, that's a movement we're trying to understand here. So, just a few words about gastrulation, but I already got a good introduction. Gastrulation is one of the first major morphogenetic events that will lead to the formation of the three germ layers, which is the ectoderm, the mesoderm, and the endoderm. And gastrulation has been worked out in many species, as you heard here, the Drosophila, the zebrafish, that you will hear hereafter, Xenopus. But it's not exactly the same for vertebrate amniotes. And this is because it's technically challenging to live image this species. So, and as I said, the cellular events have been worked out, but here mammals, it's very difficult. So what we decided to do as a lab is to work using avians. And avians have different advantages, and especially they are very amenable to live imaging methodology, which is very critical aspect if you want to have a look at dynamic processes, of course. So, gastrulation in chicken happens just when you put the embryo, the eggs in the incubator here, and the embryo is composed of a flat disk of around 50,000 cells already when the egg is laid, and upon incubation, you have this massive cell movement taking place. So cells move away from the center of the epithelial disc and move back toward the center of the disc. And this will generate the primitive streak here, which is where the mesoderm will form and ingress. So we know quite a few things about how these things happen, and the lab of Claudio Stern and Keith Waiter have worked out the cellular events that drive the formation of the primitive streak. And we know that it's a typical convergent extension event which drives the formation of the streak, and this is controlled by a junction remodeling of myosin. And while these events here are nicely explaining how you form and elongate the primitive streak, they do not explain how you get this massive rotational movement taking place within the embryo. And that's a question we really decided to understand. And I should mention that this movement takes place in an epithelium, so all the cells are connected to adherent junction. So really what we wanted to understand is how can the massive movement take place? Do the cells rearrange? If so, how do they do that in this region? And or do they change shape? So we knew very little when we started the lab. So one of the first things, I should also mention that it has been noted that this might be related to fluid mechanics. And these movements here resemble very nicely the movement that you will get of a fluid which is contained in a dish when you apply a force toward the center. And that's just me this weekend playing with my daughter, showing her some fluid mechanics. And you can really see this if you put milk in a dish and you just blow, it's me blowing here in this direction, you can nicely recapitulate these movements. So it's all, it's pretty much what we're trying to understand how during this presentation. From a physical perspective, it's very simple then, because all you need here is that you need a force directed toward the center, you need the material property of the milk to be the one of the fluid, and you need a boundary condition to constrain the flow. So this is good for a fluid in motion, but how does it relate for an embryo? So what is the force here? What is the material property of the embryo? Is it really a fluid? And what is the boundary condition? Because here you can see that the movement are confined not at the border, really. So how does it work? That's really what we wanted to understand. So when I started my lab about 7 years ago now, I decided to change from the chicken embryo, which is a widely used model, to the quail, because the quail is a smaller animal and can be housed in the lab, and also the generation time is 3 times faster. So that allows us to generate transgenic quail lines within 6 months. And we have several transgenic lines now. The one which I'll talk about are the membrane-bound GFP, which allow us to see all the boundary of the cells, and also the reporter for actin and myosin. And we have also sequenced the genome, and we're trying to make knock-in and knockouts now in the quail. But so then when we got the embryo, more than I could ever anticipate it, we got massive data. And this is a very nice collaboration between Mehdi, postdoc in the lab, and Francis Corson, who is biophysicist here at École Normale Supérieure. So Mehdi worked out all the imaging and culturing conditions to be able to live image the embryo. So just to give you a sense of scale here, this is 50,000 cells at the beginning and around 200,000 at the end of the movie. This is 3.5 millimeter in diameter, and the movie takes about 12 hours. So then, Francis, when the movie were out, we needed to extract data from these movies. And Francis designed a custom-made PIV analysis for this kind of data. And you can see the flow here, which is from the particle image velocimetry analysis. And here you see the streak here forming. And we can, from this PIV analysis, we can now have a look at deformation. So we can really get rid of the cell scale to have to analyze the tissue movement. So blue is expansion, and red here is contraction. So we can really treat the embryo as a material. So this is exactly the same data, but seen differently from the first deformation map from the first time point. And what we noted here is that now we can recognize all the different territories that have been recognized historically from anatomical landmarks. We can see that the mesoderm here is contracting, the extraembryonic tissue, which is the outer ring, is expanding dramatically, whereas the embryo proper doesn't change much its area. So what Francis did was great, because I don't have time to explain how he does that, but he designed a pipeline in order to detect these anatomical landmarks based solely on the tissue motion. And this is great because now we can feed the movie into the pipeline, and we can automatically detect all these territories, and we can fate map and we can track them. This is great for a number of reasons, and the one of them is because now we can make several movies in different, and we can treat them with the PIV, and we can get all these velocity fields from the PIV analysis, and we can realign in space and time all these different movies, which allow us to create an average reference embryo. Sorry, so that's what you should see here. So now that's not a real embryo, that's like our perfect embryo, because every intersample variation is averaged out. So this is very good for us now. So now we can have a look at more quantitatively at the gastrulation movement. And here, what we noted is that the gray region here, the extraembryonic tissue, is expanding dramatically. That's what you see here. This is the average here. Whereas the mesoderm is contracting and gradually disappearing, because it's contracting, disappearing out of the plane and ingressing, the cells ingress. And here you can see that the embryo proper does not change much of its area. So noting that different territories were displaying different behavior, Francis decided to decompose this complex flow into a more simple flow. And it took advantage about the variation of a Helmholtz decomposition, where it took the overall tissue flows and decomposed the divergent component, so area changes, into plus the rotational component, which can be perceived as the incompressible component of the flow. So then you can already see from this slide here that the area changes are nicely going to explain how the mesoderm ingress and disappear out of the plane of the epithelium, and also that the extraembryonic is undergoing major expansion mostly. Whereas these area changes certainly do not explain how you get this rotational movement taking place within the embryo. So now that was pretty good for us, because we thought that maybe we can explain simply this movement taking place within the embryo proper using incompressible fluid mechanics. So now if the first thing what we wanted to do was just check where the force that put the embryo, if it's the fluid in motion, where is this force distributed. So what Francis did was, now that we have these velocity fields, we have the velocity fields, and we can get an idea if the embryo is treated as an incompressible fluid. This is our Stokes equation, which states that there is a balance between the viscosity, the gradient of pressure, and the force that is applied externally. Then we can get a sense of where this force, which put the fluid in motion, are localized in the embryo by looking at the Laplacian of the velocity. So that's what it did, and that's what the result is. And what was surprising for us is that we could see that there was these forces localized at the boundary between the extraembryonic tissue, so the outer ring, and the embryo proper. So that's what you can see here, and these forces remain steady as the process is being proceeding. So this can be understood. I mean, this is apparent forces that put the force in motion, the fluid in motion. But we know that there are no such external forces. But this should be understood more as active tension. So really, cells contracting, which is generated the forces to put the fluid in motion, more at the posterior and less at the anterior. So now, as I said, this is not external forces, but more internal effort. So this should be understood if you follow the equation at the divergence of the active tensor. So now we have an idea of where the force could be to put the embryo in motion. And this is how it looks like. This is the force, more tension, active tension in the posterior and less in the anterior. So this is the kind of kymograph where this is posterior and this is anterior here. So you see the force building up and being established steadily. So then we have an idea of the force. Can we model the embryo now as an incompressible, as a fluid? So now this is the incompressibility, the equation for the incompressible fluid, Stokes equation. And what we did here was so what Francis did, I should say, was to take a trick and to say that this is an incompressible fluid, but that the divergence will be prescribed, meaning that this divergence is given by the area changes. So we treat area changes separately from the flow. So this comes from the data. So this is the velocity field that gives us the area changes, and then we feed it here, and then we can get an estimation now of the distribution of the active forces that will drive the fluid if the embryo is a fluid. Then we can get an idea of what would be the flow if it is driven by a distribution of active forces which is more at the posterior and less at the anterior. And this will give us the overall modeled flow. So just the take-home message here is that we treat independently the area changes and the fluid, which will be driven by a tensile margin here, as depicted in magenta. So now this is the experiment here and the resulting model. And what you can see here is that the model is very similar. It's almost indistinguishable from the experiment. We can see the flow and the formation are actually almost very similar, as I said. And the model is quantitative, so we can estimate that it's 90% accuracy of the model. Now, because we can uncouple the contribution with the model of the area change and the tension-driven flow, we can see what would be the outcome if the embryo was driven only by area changes. And you can see, as I said at the beginning, that this will explain very nicely how you get cells disappearing out of the plane and how you can get the formation of the extraembryonic tissue. But it does not explain how you get the primitive streak, whereas the tension-driven flow here would explain exactly, although the proportion is not exactly conserved, would explain exactly how you get the rotation that leads to the formation of the primitive streak. So Francis went a little bit further and decided that we can model the embryo as only a three mathematical function of time: the areal expansion, which explained very nicely the extraembryonic tissue, as I said, the areal contraction, which explained the ingression of the mesoderm, and the tension-driven flow that explained nicely the rotation of the embryo. And that's now a completely synthetic embryo. And we can see here, and you can see that this embryo now is the perfect embryo that recapitulates the tissue motion. And because it was derived from actual data, this embryo is also quantitative, and we can estimate that this deformation and flows is actually reproduce the real average embryo with 88% accuracy, meaning that here again we are being quantitative. So now this is just modeling, which explains that maybe here, because it's only assumptions, that the deformation and flows are driven by a tensile margin contracting gradually more posterior and less in the anterior in a fluid. So is it the case? So we can check that. Is there such a tensile ring? Can it be revealed in the embryo? And where does the fluidity come from? And also, can we provoke hydrodynamic perturbation if the embryo is to be considered as a fluid? So then the first thing what we did was to check whether there is actually a mechanical, to reveal mechanically the ring of tension. So what Mehdi did was to make a movie. We can infer from the PAV where the tension, high tension would be, and then we do laser ablation at different locations in the embryo. And what we can see here that when you are at the posterior, you get higher anisotropies. You have higher anisotropy, which means higher tension. But where you are outside, when you are in the anterior, where there should be less anisotropy, less tension, we see that we see much less anisotropy, and there is almost no anisotropy in the embryo proper. And this is all the cut that we made projected on one graph, and this is quantification. This is exactly what I just said. So then we decided to go more molecularly or cellularly and look at the cell deformation and at the molecular level. So, and this is just half an embryo because now that's not a 10x movie, that's more a 40x movie, and we cannot it takes too long to take the entire embryo. So you're looking just at one side of the embryo. And when I play the movie, which is a line reporting myosin TD tomato fusion, protein, we can see here, I don't know if you can see it, if I enlarge here, we could spot that there are supracellular cables surrounding the entire embryo proper. So exactly as we had predicted that there could be actual margin, contractile margin using myosin. So now we did higher magnification. This would be more in the posterior, not exactly here, indeed. And what we see here, this is myosin again. And when we spot the behavior, when we look at the behavior, we can see the supracellular cable in the posterior, which are contracting and are driving rearrangement and convergent extension, as I said in the introduction. But what was more surprising, given the introduction, but less coming from the model, is that when you look anteriorly, you see exactly the same supracellular cables, but these cables do not contract here, but they instead extend. And you see exactly the opposite phenotype in the anterior where the cells contract, and in the posterior where the cells contract, and the anterior where the cells extend. So it's exactly what we expected. So now, the force distribution looks like it's really along the margin. Now, where does the fluidity come from? So a few years ago, we identified that in the embryo, this was published a few years ago, in the embryo, the cell division was driving massive rearrangement. And this you can see here qualitatively. When a cell divides, it brings neighbors which were originally distant into contact, and the daughter cells themselves intercalate in between the neighbors. And this is very different from what has been published in other species. And now this is only one cell dividing, but you should imagine that in the embryo, all the cells are dividing, not at the same moment, but they all divide, and they drive each of these cells massive rearrangement. So, and this is a major source of rearrangement in the embryo. So if you block cell division, you can see the pattern. The stripe pattern is not recognizable from the beginning, but when you block cell division, now you can see that there is almost no rearrangement left, and they can really recognize the pattern, and the topology is conserved throughout time. So we thought that maybe cell division, by driving a rearrangement, will fluidize the tissue. So then what we did was to block cell division. So this is an average the deformation map or PAV analysis from 5 embryo in which cell division has been blocked. And what we see here is that at the beginning, the movement takes place because the drugs that we use take some time to inhibit the cell division. But what you can see here, that very quickly the rotational movement, the rotational flows disappears in the embryo. But what I like with this movie is that you can see that the extraembryonic tissue here in the blue is expanding and keeps expanding. So really, we don't kill the embryo by interfering here with the proliferation, but we actually kill the rotational component. So from the model, that means two things. Either the forces that drive the tissue motion have disappeared, or that the viscosity has increased. So in order to distinguish between the two possibilities, what we did was to do exactly like the same. So we take an embryo, make a movie, and we wait until the drug acts, and you see the rotational movement stopping here. And when we do laser ablation in the posterior, we see that there are still tension, and there is also tension in the anterior, and there is indeed maybe even more tension. So the fact that the movement are stopping in the embryo is not because there is no tension anymore. It's really when this goes along the line that it is cell division by suppressing cell rearrangement is suppressing fluidity. So now, the fluidity looks like would come from cell division, the contraction from actomyosin, and now if we go back to the initial description of the fluid, this is quite different from what we thought could happen from the fluid in a dish, because now this means that the flow is shaped by the force distribution, so the contractile ring, which is going to shape the flow. Whereas here, this is mainly the boundary condition, and fluids are very sensitive to boundary condition. So so this is a strong prediction of our model that the embryo should be quite insensitive to the boundary condition. So how can we do that? How we can test that? So this is very easy in the model. We can make the boundary condition closer to the embryo proper. So the model, it's easy. You just make the boundary closer. And the model tells us that the flow should not be much affected, and indeed the formation of the primitive streak and the rotational flow should be almost as in normal embryos. But we can do exactly the same experiment in the embryo. So we use a laser ablation now to remove most, if not most, of the extra-embryonic tissue, which brings the border closer to the margin. And then we make a movie, and what we see is exactly, there is a movie that should play also. We have no effect on the flow and no effect on the deformation, and the primitive streaks form normally. So now, this is good, but this is a negative result in a way. So we thought, actually, Francis thought that if we bring the border closer to the embryo proper to the margin, then we should have a different effect. And this is very clear on the model. So we make, if we bring the border closer to this end, we see that very quickly there is only one apparent vortex taking place in the fluid, and now we should get a bent primitive streak. And we can do exactly the same in the experiment. So now it's an off-center cut, and you see here exactly what the model predicted. The embryo is left with only one apparent vortex, and then we have a bent primitive streak. So to conclude, so what we can say is that the massive tissue flows and deformation that are taking place in the embryo are actually due to fluid mechanics, and it's can be explained by fluid mechanics, and there is a contractile ring at the margin between the extra-embryonic tissue and the embryo proper tissue, which gradually contract more in the posterior, less in the anterior, and the force is propagated due to the material property of the embryo, which act as a fluid thanks to cell division, which drive massive rearrangement in the embryo. So now to go back to keep up with the theme, is it controlled or self-organized? So now we don't know exactly the answer, so that's something we're really interested in. Okay, I'm almost done. We think it could be indeed self-organized. So I don't have data to show today, but I can give you hints why we think it's self-organized. The first thing that we noted is that the deformation and indeed the force needed to drive the deformation are steady throughout development, which means that they build progressively, but once they've built, they remain steady, and these are the forces which are indeed required to drive the formation of the primitive streak. And when we look at the expression pattern that are supposed to drive this contraction, so we know there is a rough pre-pattern, which can be, the contraction can be driven by Wnt8C, but also GDF1 or even other molecules. And we know that there is this bias right at the posterior, but this expression pattern, which are triggering the contraction, so far what we've noted is that they are advected with the flow. So it's very difficult to understand how a pattern that would be advected with the flow would induce a steady pattern throughout time. So we think that maybe the forces could self-organize once they've been triggered by molecular cues. Then also something we are very interested in is that it looks like the embryo has the potential to self-organize itself, because this brings us back to a seminal experiment performed in the 60s, where people took epiblasts, so embryos at the same stage I just talked about. And this section bisected the embryos, and what they found is that when you do that, not only you get a full embryo from the posterior half, then the embryo manages to cope with the absence of the anterior tissue, but you get some embryo, you get an ectopic embryo forming from the anterior half, where you should have never got an embryo in this place. So now we're trying to test, this is where we're going, if the force is self-organized, but also if the interplay with gene expression in order to drive embryo formation during normal development. So that's the people that did the work, that's our team. So I mentioned Mehdi, and that's been a great collaboration with Francis. And also I want to thank Didier, Rocancoindroli, and Roussel, who actually made the quell line and took care of the quell line. And also the funding bodies. And I thank you for your attention.